actually sick today. So today's speaker is Dr. Clément Grelet from Wallonie Research Center that will give a presentation related to the real field use of developed infrared models, quality aspects, and key factors for reliable prediction. So I would like to thank you and thanks Grelet for being available to give this presentation. And so I leave the floor to you, Grelet.
Thank you, Giulio and Maria. I hope you hear me well. And that's a pleasure to be here to discuss with you of some experience we have with real field use of infrared models, and especially to discuss of some quality aspect that may really impact the predictions. So my name is Clément. And I'm coming from this institution, so it's Walloon Agricultural Research Center. I see François is here. François is we are colleagues together. So we are maybe you saw his presentation some months ago. So we are working in Belgium. It's a public institution. We directly depend of the Walloon government. So Wallonia, it's the south part of Belgium, the red part that you can see. So the part where we speak French. And by the way, if you come to Belgium, you are welcome to visit us and have some beers and chocolate. So we are a quite small institution. It's only 400 staff working there, 100 scientists, but we have a quite long experience in spectroscopy. And today we will talk of mainly of milk mid-infrared spectra, because that's what we are doing with my colleagues. So for all the one of you that don't know well the topic, the spectrometry in the milk world is used every day because farmers produce milk, and the milk industry, they buy the milk to farmers based on the fat content and the protein content. And that we obtain through mid-infrared spectrometry. So it's really daily analysis in many countries, and it's fast, cost-effective, easy to use. So you know that. And it's not only used to predict the main components as fat and protein. So more and more, we predict many phenotypes. And it's mostly to manage cows, so to provide to help farmers in managing the herds, or to do genetic studies. And linked to that, the really big advantage is that you can constitute a database with millions of cows that you store from years. And when you have a new model, you can apply that model a posteriori on all those historical data, and so easily compute genetic studies. So there is really an exponential number of researches going with milk mid-infrared spectra. And just some examples to show you some phenotypes that we can predict. It's in link with milk quality, technological properties, a lot with the cow phenotypes, so health of cows, fertility of cows, and things like that. We can also detect contaminants, outliers, or the origin of the milk. Then in a lab, in what we call the classical use, a milk is analyzed in a spectrometer. It's really like a black box. We don't really, we cannot interfere with the models and so on. So there is a spectra that is produced and a model that is applied. And the people in the lab, they receive prediction for fat, protein, urea. That is used to pay the farmer. And it's mostly with 3 types of instrument, FOSS, Bentley and Delta, that has been bought by Perkin-Elmer, and then they stopped the production of instruments. So it's mostly FOSS and Bentley at the time. And so, as I said, it's kind of a black box. But what we do now since 20 years, I call that the new use. Is not new anymore, but it's to extract the raw information, so the spectra. Then in some places we standardize them as a kind of quality insurance tool. And then we are able in farmer organization, for example, to apply any type of model that you can develop. And then we can predict many types of parameters, phenotypes. So all this is done into an external server or computer. It's not anymore in the spectrometer itself. And so today we're interested in what are the key elements that impact the predictions. In our case at CRA, we don't provide ourselves prediction to farmers, but we are working in quite close collaboration with the farmer organization who provide directly prediction to farmers. So the model that we developed, they go to the field. So we want to be able to manage everything that may impact the prediction. So at least the most as we can. And then it could be a huge difference between developing a model in a research context or developing a model really in the aim of being able to have prediction at a large scale. Why? Because usually in a research context, we want to evaluate the potential of the methodology to predict something in the goal of doing a paper. So most of the time it's with few research herds, quite a limited number of cows, few diets, only one breed, potentially one country and one mid-infrared instrument. And then the model is optimized regarding performances. So we want to obtain the best R-square and the lowest RMSE. In the other end, when we want to apply a model at a large scale, I'm sorry for those stupid cars, but yeah, it's like that. The aim is really to have a model that have a capacity to face all conditions that we can meet in the real life. So really an all-terrain model. And in that way, it can be quite different of what we do in research. And actually, looking to the number of the high number of papers that are done every year on mid-infrared and milk spectra, I have no idea of what is the percentage of those models that are really applied in the field, but that should be quite low at the end. And when we speak of real field conditions, it's the model, they need to face different breeds, different seasons, different diets of cows, also different types of instruments and geographic regions and so on. So basically, maybe the most important point is to look to the reference value. It's obvious. But when we deal with wet chemistry to analyze like fat composition or something like that, we expect something really precise. So that's not that much a trouble. But when we go to phenotypes of cows, like measuring the intake of the cows, we know that the accuracy of this type of measure is really low because there could be one cow interfering with another, or they just let through the diet out or things like that. Then we know the reference is really imprecise, and the R-square, the maximum R-square that we can obtain is directly dependent of what we call the standard error of laboratory. So the error of the reference value, and then an imprecise reference value directly lead to an imprecise model. So that's something always to keep in mind. Then we create models and we will apply them on reality. And one example that we can face in research, for example, is to have a data set with only one breed. And it's something that's really happen often. It's that we have data set with only Holstein cows. That's the main breed. So most of the time in most of countries, we have data set with Holstein cows. And here we have a small example. We do a model predicting methane emission by dairy cows with 225 Holstein cows, and then we obtain that error in cross validation. But when we apply this model into another breed, so on those Jersey cows, on those 20 Jersey cows, we can see that the RMSE is clearly increasing. The model is not really able to predict this overbreed. So what we just to check, what we could do is to include 19 over Jersey cows into that model. So that's only 19 records with other cows. And just doing that, it's improving the RMECP by 19%. So it's an empirical way to see that the model face difficulties when it needs to be applied on something that it doesn't know. Another simple example of what we faced on the field is that for those who are not really familiar with cows, a cow is having a calf, and then the lactation starts. So she's starting to produce milk, and this is during for 1 year, and we call that the lactation curves. And during this year, everything is changing in time. The milk composition is changing, the milk quantity is changing, and the state of the cow is changing. But most of the time, or at least in some research, we focus only on the beginning of lactation, because this is where most of the diseases and troubles happen. So we have data sets only with the beginning of lactation, like this one, only from days in milk 0 to days in milk 100. So here we simulate a model with only the beginning of lactation, and we apply it on a data set with the late stage of lactation. And we also see that the model is facing some troubles, and that the error in external validation is really high. And if we do again the same test of including only few records from the late lactation in the model, we directly see also an improvement of the model, just because we include variability, and the model needs to be able to face that real field variability. So these were two quite empirical examples. Another way to see the thing is regarding the variability of the Y, so the reference data. So in this example, we take a model predicting, well, let's say, with reference data on nitrogen efficiency of dairy cows. And when you look to the literature, the nitrogen efficiency of cows is supposed to range between 10 to 40%. So we do a model with those data, and we are quite happy with the RMEC. But then when you apply the model in the reality, you also face extreme data. And here you can see how the model is performing with external validation data, the red one, that are extreme data. And directly you see that there is a strong slope error on those data, because the capacity of the model to extrapolate is quite poor, because it don't know those data. And the RMECP is increasing to 11%. So again, one idea would be to increase the variability of the model with those extreme data that you are not that much supposed to face in the reality, but that exist. However, the RMEC, you can see it's increasing from 3.5 to 5.2%. So one doing research will think, okay, I will not include those data. It's the accuracy of my model is not good enough anymore. However, when you test again with those extreme data, it's clearly improving the results. So that's really a challenge that we can have between the apparent accuracy in cross-validation, or with a small data set, and really the robustness of model that provide capacity to handle any type of data in the reality. This is another example with real data. This is a model where methane is predicted, and here you can see that the data depending of the country where they were collected, and you can see that the range depending of the country is quite different. And in that case, the only low data were coming from Ireland. So it means that without the Irish data, each time you are supposed to have a low value, you do extrapolation. So without this international collaboration, without the Irish data, we will not be able to cover the low part of the value. So that's really a way, when the data are really expensive to find and difficult to collect, to collaborate together to find as well the variability that we will meet in the reality. Then, if this is the case for the Y, that's probably the case for the X side of the data, so the spectral range. So let's imagine we have a data set composed by 3 countries. These are spectra plotted in a PCA, and we have a new sample to predict. So what people usually do is they look to the Mahalanobis distance. We usually look to the standardized Mahalanobis distance, so with what we call the GH. So this is the distance of the sample to the centroid to the sample, and then usual quality assurance system is to say if the GH is higher than 3. So as in any type of distribution, when you are more than 3 times the standard deviation, you consider the sample as an extreme one. When the GH is lower than 3, so you can consider the sample is, let's say, covered by the calibration data set. So you can think the model is able to handle that sample, so that's fine. So that is quite common. But now the question is, in the calibration data set, do we want those extreme samples? And in a quite large majority of papers, there is a kind of cleaning step saying that when I am excluding all the samples with GH higher than 3. So majority of research work, those extreme samples are removed. But if we think to this story of extrapolation, that may be of interest to keep them in the data set. So to check that, we did a small test. We took a data set with lactoferrin data. So lactoferrin, it's a molecule in milk that is a biomarker for health of the cow, let's say. And we have a global data set of 3,500 data. So it represents global population, like in a country, for example. And then we want to develop a model. We cannot sample all the population, so we select only 200 samples. And we did 2 types of selection. One is a random selection, and one is an oriented selection, really to find the extreme spectra, really to be able to cover the variability in the data set. So we only take the extreme spectra in that selection. And then we perform an external validation with 400 other samples that were randomly selected. So if we look to the result first, so we have on the top the random selection and then the extreme selection. If we look first visually doing a PCA with the global data set and the random selection, first we observe that visually the extreme selection better cover the space, the variability of the global data set. Then when we do a cross validation, the error for the random selection is clearly lower. So again, someone in research could think, okay, I will take that one. I will take the random selection. It's clearly more accurate. But again, in external validation, the error is clearly better with the extreme selection. So it means you put samples in the data sets that are quite extreme. So it's maybe not the one that are with which it's the most easy to do the model, but when you really apply the model in the real life, they are potentially the best one because they will cover the reality. And the RMIC is decreasing by 14%. And why? Because in the extreme model, let's say, only 1.5% of the validation sample are not included in the dataset, and it goes to 6.6 in the random selection. So it's really the capacity of the calibration dataset to cover the real variability. So before to go to the next step, maybe 2 things that are good to keep in mind with spectroscopy is that infrared model can only predict what they know, and extrapolation is dangerous, and that's why we think we should keep as much as possible information in the calibration dataset. And when the information is really difficult to find, then collaboration is really a good way to fill the gaps. Then another aspect is which wave number to use, and does it imply the robustness of the models and the quality of prediction in the daily use. So first, simple aspect is quite obvious, but when you have two types of instruments and you want to develop one model that will be applied on everything, you need to work on the common range. This is also quite obvious, at least you have not really the choice. But again, with so many research working with the full range, it's fine as soon as you are doing research, but when you want to apply it, then you have at least to be on that common range. And then when you are on that common range, you have those noisy area. In spectroscopy, usually we consider that we are not using them because it's too noisy or it does not contain information. So it's a common way of not using them. However, there are quite a lot of research, at least with mid-infrared spectra, saying that there is information in those regions. So it's changing a bit the game in that area. So the question now is not, is there information, but if there is information, can we use it or should we use it? So what we did to check that, we took 83 instruments, majority of FOSS, 10 Bentley and 1 Delta, and to all of them we sent 5 identical milk samples. All the instruments received the same milk samples. And then we took one instrument as the reference and we look to the correlation at each wave number between the absorbance value of the reference and the other instruments. And if the information is the same, or at least if it's mostly the same, it will be correlated. If there is no correlation, then the information is not the same, or there is something different. And the results are looking like that. So there is in black one milk spectrum, so just to see where we are in the milk spectrum. And then you have the correlation for the FOSS in blue, the delta in orange, and the Bentley in red. And then you can discriminate different parts. So let's say the black parts where the correlation is low for the majority of spectrometer, the gray part where it's low for some of the spectrometers, and the white part where the correlation is really high for all of them. And then we can do model with all the wave numbers, or only with the gray and the white part, or only with the white part where the correlation is really high, and it leads to 212 wave numbers. Then to check that, we did a model with oleic acid, only keeping few samples in the calibration to have 1,500 in the external validation. And I'm sorry, I don't have the exact number in mind, but I think it represents like 20 instruments in this external validation dataset, which is important. If you validate only with one instrument, you cannot see the difference anymore. And then we do the model in calibration. So here it seems that the model 2 and 3, let's say, have similar performances, and the one is clearly not that good. But when we do an external validation, we can see that the model with the really only focusing on the information that is repeatable across the instrument is providing the best result. So yeah, the conclusion to me could be that there is probably information on those noisy area, but can we use it? Yes, if it's only for research, or if it's a genetic study with 1 or 2 instruments, but no, if the goal of the model is to be applied on a large variety of instruments in practice to provide information to farmers. Why? Because if there is information, it's not reproducible between instruments. And then when you apply a common model to that, of course, it will lead to some troubles in the predictions. Then we come to that point of instrument to instrument variations. So here to test that, we took a model predicting the polyunsaturated fatty acids that have been developed in one instrument. And after sharing one common sample to 66 other instruments, we looked to the predictions. So you can see the prediction of the, let's say, what we call the master, the reference instrument on the left. Then the prediction of all the other instruments without any standardization, and the prediction of the same instrument but with standardization, the same 66 instruments. So here, the standard deviation has been reduced 5 times, standardizing the spectra, but especially you can see the prediction without standardization. So if with one sample you obtain a so large variety of prediction that are really totally different, then you can imagine that you cannot provide any information to a farmer or an industry without any standardization. So as it's the factor impacting the most the prediction, we detail a bit more that aspect. So the basis for that is that there is strong differences, of course, between the brands of instruments, within the brand and within the model within a brand. So all the instruments are different. So of course, between two brands, here is two instruments of FOSS and delta analyzing the same sample. So it's obvious it's different. And when we apply a common model to those spectra, of course, it provides different predictions. And if we plot those predictions to have a better representation, we see it's really totally different, and there is even no correlation between the predictions. So it's quite obvious, but it's not possible to apply a model developed, for example, on a FOSS, on a Bentley or on a delta instrument. However, even between two instruments from the same brand, so here it's two FOSS, if we look just visually, it's not that obvious that there are differences. You don't see that much differences on just looking like that. So when we apply again a common model to those two instruments analyzing the same 5 samples, we still see a quite large difference. Again, if we plot that, we see there is both a slope and an intercept deviation between the two instruments. So even between two FOSS, if you apply a model from one instrument to another, there will be troubles in the predictions. And another way to see that is here we took 45 instruments from the same brand. We sent them 5 identical milk samples, and then we just did a PCA on the data, only on the informative wave numbers, so removing water and so on. And you can see that each symbol is one instrument. So just visually, it directly explains that each instrument has a proper signal response, and they are all different. There is really a large variety of spectral responses. And on top of being different each others, they are all drifting in time, not that much drifting, but their response change in time. And this is normal, and it's just due to changes like the conditions in the lab, temperature, humidity. Each time we replace a piece, both in the optics or even the homogenizer, it has an impact on the response. Each maintenance operation has an impact as well. And just the use and the wear of the instrument is changing the response. And to see that, what we do is we analyze on 3 months basis batches of identical bottles of UHT milk. So during 3 months, you have the same batch of milk that is analyzed every day. We get the raw spectra, so without any standardization. And on those raw spectra, we apply just a simple fat model. And then the milk is the same over time, at least each 3 months. And the model is the same. So when we see perturbation like the one we see on the red batch, it's meaning that there was a perturbation on the spectra of the instrument. So in this example, it was a maintenance operation. And here it's another example. Here it's not a one single perturbation, but it's more a drift in time. And that could be more in link with changing in the path length in the cuvette or something like that. So this is not that much a trouble in the daily life of the labs, because when we mention fat, protein, lactose, and everything like that, what they do is that they analyze standard sample with known reference value, and then it's really easy for them to correct the mid-infrared prediction to that basis. And so they can do that once a week, and then every day and multiple times in a day, they check the bias. So the predictions are fine, and it really erases the differences between instrument and the drift in time. However, when we come to those new phenotypes, like direct phenotypes of cows or blood components, or even the small molecules in milk, it's sometimes really complex or really expensive, or even impossible to create standard sample with known reference value. Then for that, we need something else, another solution. Another way to see the thing is that you have a sample, a spectra is generated by that sample, and then you obtain classical prediction in the lab. And we can adjust those predictions based on standard sample with known reference value. With the new prediction, we would like to do that, but it's not possible anymore. So what we do is we harmonize directly the spectra through the way of the spectral standardization. And the goal of that is really first to create common models by sharing data from different places, but most of all to use the models to be able to have correct prediction in time within one lab, comparing different labs, and providing correct prediction to farmers. And as we do it monthly, it enables also to have stabilization of the instrument in time. So to represent that, how it's working, let's imagine this is a network of instruments with different brands. You have differences between the brands, but also within the brands. And we have one instrument that is considered as the reference. We call that the master. And every month, all of the other instruments are harmonized to that master. So every month, all the instruments come close to this master. It's not exactly the same, because it's only a transfer. We always still have some differences, but then it's close enough to create common models with the spectra of the different instruments, and especially to use the models on all the instruments. So basically, for that, 5 samples of milk are shared to all the instruments participating to the standardization. And it's done every month, and at the moment it's a bit more than 100 instruments. And then when we get back all the spectra, the methodology used is the piecewise direct standardization. It's quite simple. It's only harmonize let's say, all the instruments to the master, wave number per wave number. And then if we go back to that picture, we have the same here. So you can recognize the blue ones that are still the same. So the instrument before standardization. You have in red the master in the middle, and in green all the blue instruments, but after standardization. So here you directly see the impact of the standardization. So it's not equally the same as the master, but it really brings them close to the master, close enough to be able to transfer models. And here we have an example with numbers. So you have this example of the methane model applied on 2 FOSS instruments before standardization with an RMSE of 200 grams of methane per day. And then the same instrument after standardization, and the RMSE is decreasing to 21 grams of methane per day. So if you think back, let's say the RMSE of the model is 60 grams of methane per day. Here we had a small error due to transfer, which is 20 compared to 60. So we consider it's small enough to transfer model between instruments. And last slide is just to show the practical impact of that. Here we have that methane model analyzed, applied on fourth German instrument that all analyze a common milk, and you have the prediction by the master, the prediction by the slaves, the 8 instrument without standardization, and you can see the standard deviation is 86 grams of methane per day, and it's decreased to only 14. So it's decreased to 3%. So the reproducibility within the different instruments decreased to 6.3%. So as a conclusion, these are only a specific example with specific data sets. So it's really not something very strong, but it may highlight some elements to take into account when really we want to apply models at a large scale. So I would say, look for variability to avoid extrapolation. It seems to be better when the model covers everything, has the capacity to cover the real situation that we can find in farms. And for that, sometimes it's almost impossible within one country to cover everything, especially if we think to blood composition or methane or everything that is really complex to collect, and then collaboration within institution and within countries can be really a key element. And we are at CRA really open to any type of collaboration. So if you have data sets and we have common phenotypes that we could share, we are really open to that. Then it's important to keep in mind the robustness and not the short-term performance, not overfitting the model to a small data set that will be difficult to generalize on a large scale. And we have to look also for common information across partners and instrument to rely only on what we can transfer from instrument to instrument, for example. And of course, if the prediction at the end come to the farmer standardization is really a key element to avoid wrong predictions in the daily life. If you want more details, most of those things are in that paper, so you can have a look. And finally, I would like to thank you for your attention and the opportunity to present what we are doing.
Very good. Thank you very much, Clément. I think it was a wonderful presentation with the many topics touched during it. I would like to ask to the audience if there are any questions. In the meanwhile, when you think to some questions, I have one for you, Clément. I think it was very interesting when you showed the addition of a very little number of Jersey cows samples to a calibration data set made up of many Holstein milk sample. And the thing that was very interesting to me was that if you add a little number of Jersey, then your R square in cross validation drops, well, or the error increase, but in external validation, the error gets reduced. So I think it was a very nice example. So my question is, do you think, based also on what you have showed, that people should develop different models for different breeds, as sometimes it is said, or do you think there should be one model for everything? I know it's a million-dollar question, but
no, but it's a good question. We are asking ourselves sometimes the same question. There was one paper from a Danish guy, Skilden, in 2014, really showing that the covariance between the Jersey milk and fatty acid and the Holstein cows and the fatty acid was different. So it would make sense to do one model per breed, but then you have to think to one model maybe per diet or per country, and at the end, I'm not sure it's feasible. And maybe even considering that, there could be a solution with in having one model. I explained in our colleagues working in near infrared, and Maria, you know that quite well, by the way. They now have like 70,000 spectra in their data set, and at the end they work with feed analysis, and they mix everything, maize, wheat, every type of feed, and they use local models. So they have a really big data set with everything inside. And when they want to predict a new sample, they look for the samples in the data set close to that sample. And they develop a specific model that will fit to that new sample. So you can imagine to have a data set with everything. And then you want to predict a Jersey cow, and the model will look to the similar samples that probably will come from Jersey cows, and then there is one model specific to that sample. It's quite time consuming when you do daily in resources, when you do daily prediction, but it's clearly a possibility.
Yeah, that's a very democratic answer. This one. Okay, thank you, Clément. I see that there is a question also in the chat from Georgiana. Georgiana says, very nice talk, thank you. And can you discuss a bit the aspects of standardization? You mean data standardization? Just to make sure I understand that part right.
Okay, I'm not fully sure to get the question. So Georgiana, you correct me if I'm going in the wrong direction. So what we do is we standardize instruments, and then per instrument we create a standardization coefficient. We do that on a monthly basis, and those instruments, they are generating in routine spectra, daily thousands of spectra, and on all those new spectra, we apply the standardization coefficient, and every month the standardization coefficient changes. So at the end, we generate data, so really spectra themselves, that are standardized across time and across instruments. Was it the answer you expect?
Okay, thank you. Yeah, I understood now. Thank you so much. Just to add very quickly, some of the things you mentioned were we found in a data challenge we participated in, including extreme, removing extremes as outliers. We found that actually training with the extremes gave much better results in the test data. So very interesting insights. Thank you so much.
Thank you. We don't like to see our RMEC increasing that much, but it's maybe the best option when we want to use the models.
Okay, so thank you, Georgiana, also for your question. There's another one in the chat from my colleague Angela Costa. Angela says, great talk, thanks. Based on research done so far by your group and related networks, which can be considered as the gold standard for methane emission in lactating cows? Are sniffer interesting?
Hi, Angela. So I'm not an expert in methane, but from the discussion I have with my colleagues, they still consider the chambers and the SF6 as the gold standard. And from what they have tried, so it was a collaboration with INRA in France, the value they get from the green feed is not. They don't reach to get the same accuracy in doing mid-infrared models that with the chambers. And even if the number is really high. So it will be probably yeah. There is this balance between the number that we will get with the green feed, but you will lose accuracy. So it may be a way to cover the variability of many countries and feed and so on, but it's not as precise as the chambers. So if to my opinion, if we can continue with the chambers and SF6, it's the best option.
Yeah, thank you, Angela. Yeah, I think this is an issue, this one, as if you, how would you deal if you collect, say you have a calibration dataset of 900 milk samples, then you have 300 milk samples with collected from a cow whose methane emission is measured with a respiratory chamber. Then 300 per methane is measured with a sniffer, and 300 with a methane measured with a green feed. So you have three different, say, instruments to collect your reference value. So this can be a challenge also.
Yeah, and Amélie Van Leer, my colleague, she have tried to see if there are correlation between chambers and SF6 and green feed, and it was only with a low number of data, so I guess it's not robust enough to make conclusion. But at the moment, what you observe is that the correlation is really low between the methodologies. So at the moment, they don't find a way to collate all those data. So it may mean that the real phenotype is not the same. So at that moment, it's quite difficult to merge them into a common data set.
Yeah, this is an issue.
Yeah.
Are there any other questions from the participants?
So it's something I already a bit discussed with Clément, but what if I have data from two instruments that don't belong to the same standardization process? I mean that we don't send the sample to standardize to the same group. So I have flow spectra from one group, one spectra from the other group. You don't have possibility, or at least it's standardized in the way you described. Is there any other way I can develop some predictions?
Yeah, in that standardization topic, we have been trying many things in internal research, and there are quite a lot of methodology. For example, you can have a look to the methodology that FOSS is using based on the equalizer, and it's a chemical sample, so this one is quite easy to share from one place to another. But when you do that, the standardization is not as precise as what we can do with milk sample, and especially with 5 milk samples. So and you have also the possibility to do what Valentina Bonfatti developed in Canada, doing the retrospective standardization based on the data set. But on this one, the trouble is that you assume on the basis that you assume that the data set are the same. However, when you have, even in one country, first the cows can be different, you can have different diets, you can have different calving season and things like that. So I think you have quite some plan B. It will be better than nothing. It will not be as precise as sharing milk samples, but it will be better than nothing.
Thanks.
Yeah, it's maybe not good news, but
okay. Are there other questions or comments from the audience? If not, I think Clément we can say thank you very much for your availability and for giving this wonderful presentation. I enjoyed that a lot, and I'm pretty sure that also the participants and the audience has enjoyed that as well. So thank you very much, and see you for the next monthly meeting.
Thank you, Alex.
Bye-bye.
Bye.
Thank you.
Thank you. Bye.